All right. So the next thing is that to commuting. So these are commuting operators. Just as non-commuting operators are important, commuting operators are also important. Two commuting operators can have simultaneous eigen bases, or bases, I should say. Okay. So what do I mean by that? So suppose that you have two operators, A and B, and they commute. So they are Hermitian. And they commute. Now suppose that you have some eigenbases for A. So A acting on, say, A of M. So A acting on AM gives me AM, right? Now consider the states that you get by acting the B operator on this eigenstates. So now I am going to ask if this is an eigenstate of A. So in other words, I apply A on it. But you see A and B, they commute. So I can write this as AB. So this is, by the way, the fact that I can go from associating these two things to associating these two things is known as the associativity principle of quantum mechanics. And then, because they commute, I can write this as BA okay? And then I can say B, A acting on A of M. But what is this? This is AM, AM, right? So AM can be factored out. So what we have proved is that B acting on AM gives me a vector which is still the eigenvector of A with the same eigenvalue. So that means that this vector must be proportional to the vector AM. This means that B acting on AM must be proportional to AM. Otherwise, A acting on this would not give me A times the same vector, right? Let's give this proportionality constant a name. Let's call it, say, BM. So this proportionality constant is the eigenvalue of the of the B operator. And we can label now this state as AM, BM by the eigenvalues of the two operators. Okay? We can label it like that. So these states, sorry, I just write psi without thinking when I'm teaching quantum mechanics. So these states, AM, BM, they form simultaneous eigenstates of the A and B operators, okay? Another more formal way of saying that, we can do a spectral decomposition of A in terms of, say, AM, AM, BM, AM, BM, and B as BM, AM, BM, AM, BM. Okay? Kabish? Anything? This is like very, very easy and trivial, but it's not, because these things are also have very deep applications, as we shall
So
see
what
when
are
we.
the, like,
Yeah.
can you give an overview of the applications of these two?
Yeah, applications will come next class,
Oh, okay.
or the rest of the course. There'll be lots of applications of simultaneous. So so for example, the idea is that suppose you have a system which is, say, rotationally invariant, right? What it'll turn out is that it's Hamiltonian, and the rotational operators will then commute.
Mm-hmm.
Okay, so, or one of the rotational operators will commute. So that will mean that there could be, the energy eigenvalues, energy eigenstate, so a state with definite energy, but it can have, say, different angular momentum. Say this can have, say, plus MEN, or there could be another state, say, with hang on, let me just say there could be a state with, say, spin up, and it's going to be, say, h bar by 2, and there is, suppose, another state with spin down which has the same energy, but its angular momentum or spin is different, right? So that's what this is saying, right? So you will see applications. Okay, you will see lots of applications. Okay, anything else?
No, sir.
Okay, so that's, I will probably not be able to cover everything I wanted to cover in this lecture, but that's okay. I will take up a little bit of time in the next lecture. Okay.
Sir, like in the point when we said that B acted on the eigenvalue of AM is proportional to it, so was non-degeneracy a presumption there, so that it's a scalar multiple of the eigenvalue?
Yes, there was. Sorry, I glossed over that point. I did not introduce the idea of non-degeneracy. So what Nai is saying is that suppose B acts on some state psi 1 with some eigenvalue B, there could be another state psi 2 linearly independent, which when acted on by B gives you the same, the same eigenvalue. Now it turns out that you can, in such situations, you can always take a linear combination of psi 1 and psi 2, say C1, C2 being the coefficient of linear combination, such that, so you get chi plus and chi minus, such that chi plus and chi minus belong to different eigenvalues of A, and therefore chi plus and chi minus are orthogonal. Okay, so that's a subtlety that we will encounter down the road, but we don't have to worry about those things now. Okay, good. All right, any more questions? Very good question, right? All right.